This demonstrator is intended to present a smart mirror application, as it has been developed in the context of Clever project, more precisely for the use case for augmented reality for shopping sites. First, this presentation will start with an introduction of the Clever application and its components, as well as use case 4 and the project's objectives that this demonstrator is aimed to cover. Then, it will provide some background about smart mirrors, in terms of demand and possible applications, as well as a general overview of its architecture. The demonstrator will present the application in its basic portions, presenting how it works, and which hardware and software components are currently employed for it. The demo will show the deployment report of the smart mirror application and how it responds to the use case's specific KPIs. Finally, an on-field deployment of this application will be reported. The Clever application consists in an application layer, different middleware components, managing various resources, and then on the bottom we can see the hardware and network layer. Use case 4 is aimed to exploit some of the resources included in Clever application, as highlighted in figure. This demonstrator in particular will focus on network accelerators and GPU virtualization, as they represent a powerful resource to handle data exchange in a distributed application scenario, while granting low-latency communication. More in detail, the use case 4 aims to develop a service to support and enhance shopping experience, based on local data acquisition from the user and low-latency processing. This service may act as an assistant, providing feedbacks, guidelines and targeted suggestions based on customers' activities. This kind of service must grant low latency and good image resolution to be able to guarantee quality of service and quality of experience to the user, and it must be able to do that even in congested scenarios, where resources exploitation becomes crucial. It must also guarantee privacy to the user and a solid level of security on any sensitive data collected during its utilization. This demonstrator exploits the potential of edge computing to improve resource management in a distributed scenario, exploiting low-latency communication to deploy different portions of a single application to different hardware components. Furthermore, it leverages on specific hardware components such as GPUs for AI and image processing, exploiting hardware resources to guarantee quality of service and quality of experience to the users. Conventional in-store shopping could be quite time-consuming, especially in very populated areas, for example, malls, due to crowded stores and in particular for the often long queues at the changing rooms. Customers and retailers are then searching for innovative solutions to improve their experience, and smart mirrors may represent one of them. Smart mirrors act as digital changing rooms, allowing customers to virtually try clothes without the need to use an actual changing room. Smart mirrors also have the potential to improve space and inventory management for retailers. Finally, smart mirrors offer the ability to try numerous garments in no time, while granting better safety for the garments themselves, which will not be exposed to any risk of damage, loss or theft. Thus, a smart mirror application allows the user to virtually try clothes, gaining visual feedback on how they would fit. To do so, the application collects a picture of the user and merges it with a garment selected from a catalog. The result is showed on a screen, acting as a digital mirror. As said, the application could offer an improvement to the shopping experience, reducing queues at fitting rooms, or it could enhance online shopping. The application developed for this demonstrator will now be described in its portions. First of all, the smart mirror need to collect an image of the user. The image could be recorded using a dedicated camera, taking a snapshot as shown. Alternatively, it is possible to upload a picture into the smart mirror application. In both cases, the subsequent image processing will be the same. Now the image can be processed. This step is necessary to recognize the human figure in the picture and its pose. The application assesses the user's body segment's position in the 2D space of the picture, creating a body map that will be necessary for the subsequent virtual try-on. These result images, namely the reconstructed pose and the body map, will be used to combine the original picture with different garments. Now, the user is ready to virtually try on any desired clothes from the catalog proposed by the application. Users could try any number of clothes, and trying new clothes does not require to reprocess the original picture, as the necessary data, namely, the segmentation map and pose, have been already acquired. This makes the process quick and easy to use, granting a comfortable user experience and an effective alternative to physical changing rooms. The algorithm used to combine clothes images and user's image is based on convolutional neural networks and has been developed to result resistant to different body frontal positions, given a good level of lighting or a low level of background noise. The application described so far could be employed in physical stores, and in case of very crowded scenarios and high number of inquiries, it will require careful handling of its resources to face the computational load. To deal with this challenge, it is possible to split the modules involved in the application into separate machines, exploiting RDMA-based data transfer to obtain low-latency communication and fast responses. Traditional TCP is reliable in ensuring data integrity and accurate delivery. It offers error detection and correction mechanisms as well as flow control. However, as shown in figure, it requires data to be copied in a buffer, which requires time and CPU usage, increasing latency. RDMA, on the other hand, transfers data from one memory to another without involving the CPU. In doing so, it can enhance performances and efficiency of data transfer between nodes in a network. RDMA-based communication provides lower latency than TCP transfer during read and write operations. This allows for low latency transfer between servers and opens to efficient distributed applications. RDMA-based communication has been used for this demonstrator to split the computational load of the Smart Mirror application between two servers, while granting low latency. The application is designed to work in a distributed environment and to employ specific hardware resources, such as GPUs, both for image preprocessing and for the output creation. While having a GPU on each node would be overly costly, a GPU virtualization system would allow the nodes to leverage from a single, remote GPU. GPU virtualization allows to have just one GPU on one node at the edge and yet have it available for any other node. When a process requiring GPU is issued on a CPU-only node, it may access to the remote hardware through custom libraries, acting as a virtual GPU. The demonstrator consists in a web application, deployed through two Dell EMC R740DX PowerEdge servers. The front-end node is where the application is launched and where data are initially collected and processed. Users may access the service through a HTTPS link, enabling their own cameras to collect pictures. The back-end node is equipped with a NVIDIA Tesla T4 GPU, and here are provided information about the available garments to try and the algorithms to merge users' pictures with selected items. The back-end node produces the final output and send it back to the front-end node to show it on screen. The two servers exchange data back and forth through RDMA-based communication. About the software components of this demonstrator, the web application has been developed using VTreact. Users' images are processed using OpenPose to assess their posture and recognize body keypoints. A 2D human parsing algorithm is used to create body mappings. All these components leverage on GPU-related libraries, thus, they exploit the GPU virtualization service provided by gVirtus. For what concerns the creation of the final image, the application Viton has been used to produce the final output. Viton is an experimental application that exploits convolutional neural networks to generate images, combining people and clothing pictures. This demonstrator is based on an existing version of the model. Both nodes have been equipped with RDMA dedicate scripts to handle transfer in both directions. Here is depicted the full deployment of the application. When the user uploads an image, either via camera or using the dedicated function, the image is collected by the front-end node. Here, the image is processed. The processing procedure runs OpenPose and the human parsing application in parallel to extract the pose, the body keypoints and the body mapping of the user. Results are shown on screen for information purposes. Image processing performed by the front-end node here leverages on GPU virtualization provided by the gVertis component, allowing the application to provide results more efficiently. Then, these data are sent to the back-end node through RDMA transfer. At this point the user is provided with a catalog of garments to try. When a new garment is selected, the Vuitton application is run on the back-end server, combining data from the user and the desired garment. After completion, the output result is sent back to the front-end node, through RDMA transfer, in order to be shown on screen. This demonstrator does not consider any interaction with the cloud, but for future developments it is aimed to develop an interaction between it and the back-end server for the exchange of statistics. The application has been optimized, exploiting at best its hardware and software components. The optimization process allowed us to reduce latency associated with each of the image processing tasks, granting an overall better user experience. The current version of the application employs only 6 seconds to complete the 2D human parsing task and is able to finish the OpenPose process in no more than 12 seconds, against the original 40. These improvements are related both to algorithm optimization and to the integration of the gVertis component. Finally, also the Vuitton application has been improved, almost having the processing time to produce the final output. The Smart Mirror application presented in this demonstrator meets the use case KPIs. The application showed the ability to collect and process an image in about 15 seconds and produce a result in about 10 seconds when a new garment is selected. These numbers are low enough to grant good quality of service and good quality of experience to the users. The use of RDMA-based communication helped in lowering the computational load, allowing for each server to take multiple requests at the same time while keeping the end-to-end latency low enough to not deteriorate the quality of service. Tests in congested scenarios may provide useful information about the potential of this infrastructure design. The application employs AI at the edge and exploits its hardware components to run it with fast responses. Finally, it could be noted that users' data are kept on the edge node and never sent to remote servers. Also, any exchanged data is detached by user's identity. Thank you for your attention.